Welcome to today's webinar on performance and efficiency aspects of electric vehicles. This is the third of 9 presentations in our battery test and measurement webinar series. Our presenter today is Andrew Halfpenny. Andrew heads technology and innovation for HBK's nCode product brand. He holds a PhD in mechanical engineering and a master's degree in civil and structural engineering. Over the years, he has introduced many new technologies to the automotive, aerospace, and power generation sectors. These include customer usage monitoring, target customer analysis, proving ground correlation, accelerated laboratory testing, and mathematical simulation. His most recent work has been developing methods to measure and improve the performance, durability, and reliability of electric vehicles. Andrew is also a visiting lecturer on structural dynamics and structural health monitoring with the University of Sheffield. Andrew, it's all yours.
Thank you, Krista. And welcome everyone to our third webinar. So this one's titled Performance and Efficiency Aspects of Electric Vehicles, and in particular looking at batteries and electrical systems. So just to remind you, this is a 9 webinars in this series, and I'm dealing with the first 4. So we had an introduction to batteries and electrical systems in the first one. Then last Thursday, we looked at mechanical and durability aspects. And if you want to, these are available on the back catalogue, if you like, if you want to watch the recordings. Today, we're going to look at performance and efficiency. And then it would be really nice if you could join us on Thursday to also look at the reliability aspects as well. So what we're looking for here then is, in an electric vehicle, energy is transformed from one state to another and back again as well. And each transfer through state incurs efficiency losses. Now, if we can measure those data and analyze them and look at those efficiency losses in detail, it means that we've got a better chance of improving the efficiency. So for me, our story this week is going to start with this wonderful eDrive system from HBM. And this is a really high-speed data acquisition and analysis system. And it can capture all of the EV data, as we'll see in a minute, so we can start to analyze them. And the eDrive system has analysis capabilities on board as well, which run in real time. However, I'm also going to be talking about the analysis that we can do as a post-process, because in post-process, we're not constrained by real-time systems. So we can throw more aggressive and powerful analyses at these, and even do things like look at the power, really at the frequencies of the switching, the digital inverter switching. Also, we don't have to worry about things like assumptions of sinusoidal waveforms and the fact that these are not steady state, but they're very transient. They depend on where your right foot is when you're driving. So again, we'll have a look at that too. So this is handled in our nCode software, and we'll also have a look at some other things that nCode software can do as well. It doesn't only work on data from the test laboratory, but we can actually analyze real data from real vehicles and customers as well. So I'll have a quick look at that too. But let's start off by looking at the eDrive system. So I'd say the eDrive system is a fantastic piece of kit. It's a really high-speed data acquisition and analysis package. It can record data up to 2 megasamples per channel. It's really accurate. It's got auto ranging on those to make it easier to work with as well. And it can collect all of the electro and mechanical signals in one. So when we're looking at this, we can collect DC voltage and current here from the battery. At the same time, we can monitor what the CAN bus is saying to the inverter. We can calculate and measure the voltage and current from the AC inverter. We can go through the electric machine, and we can actually measure using HBM's torque cells, the torque and the speed that's coming out. So all of that can be done really quickly. And it also means then that we can actually do the transient power measurements. So we can calculate to the worldwide harmonized light vehicle standards and things like that. And it can also pass feedback to a control system as well. So it's an amazing piece of kit in its own right. But of course, as well as doing analysis on board, it can log those analyses, and that means that we can do further analysis later. So this is data. This is coming straight from our eDrive system into the nCode software, and we've got a new glyph here called the electric power glyph. And this is taking these data from eDrive and it's calculating the efficiency maps that we see down here. So by understanding the data, by understanding the power in greater detail, we can start to look at that. We can play what-if games, and we can try and quantify and improve our inverter to get better efficiency out of it, diagnose problems and troubleshooting and things like that. So this is the key thing, and obviously the efficiency maps are what we're seeing. So how do we calculate that efficiency then? Well, the efficiency is all based on calculating power, so instantaneous power, and then sort of averaging it, if you like, to find the energy. And if we look at this, some of them are really easy, aren't they? So DC, for instance, power is just voltage times current. So that's quite simple. And mechanical power as well. It's hard to measure, but we can do that with the HBM transducer. And then if we take the torque multiplied by the shaft speed, that gives us the mechanical power. So we've got mechanical power out of the motor, mechanical power out of the gearbox at the end. So we can look at the efficiency of the gearbox. We can even calculate kinetic energy as well, the power using to propel the vehicle, and I'll talk more about that later. But these three here, these are what we get in the laboratory when we're looking at our eDrive system. The complicated one is actually AC power. Now, this is much harder, and that's because really the current and the voltage aren't always in phase with each other. They can be slightly out of phase, and that creates sort of a negative power, if you like. So the engineers, when we're dealing with this, it mostly comes from power grid usage on the AC power grid, and our waveform there is sinusoidal and it's three-phase. And the engineers talk about three types of power. We have the apparent power, the active power, and the reactive power. Now, the apparent power is the total power that's provided by the source. The active power is the amount of that which is actually doing useful work. So this is consumed by the resistive load. It's powering our lights, our heating systems, our production line equipment, and so on. We also have this third component, reactive power. This is useless power, if you like. It's the power that's created, or the difference between the phase of the voltage and the current. It's not consumed by the resistive load, but it introduces negative power on the grid. So that offsets the grid power. So we usually end up paying for that as well. My colleague here drew a very good picture for this. So thanks to Kurt for this. His view here is that if power were the caffeine content of your favorite drink, then the apparent power is how much they're selling you. It's the volume of your cappuccino in the cup. Actually, the active power that's coming from the caffeine of that is actually covered by this little bit down here, this bottom part, and the foam on the top is mere decorative, and that's the reactive power. So it appears that you're getting quite a lot, but a fair bit of that is just froth. And that is a similar analogy really to what we're seeing. So I thought I'd present that to you because I thought that was a really good analogy. Now, of course, when we're looking at AC power from an electric vehicle, it's not smooth and sinusoidal. It's actually done through a digital power inverter. So now the waveform, rather than being three-phase sinusoidal, can be multiple phases. They're definitely not sinusoidal. And the amplitude and the frequencies vary all the time. They're transient and dynamic. But as engineers, we still want to deal with the apparent, reactive, and active power. So again, our apparent power now is the total power provided to the motor. The active is that that's consumed in actually doing useful work in the vehicle and driving our wheels. And the reactive power is not consumed, but it does cause efficiency losses. So the higher the reactive power, the more losses we're going to get. So as engineers, we want to minimize the reactive and maximize the active power. That's what we're trying to look at. So if we look at this, as the data's coming off of our eDrive system, we see here, this is the current, and it's nice and sinusoidal. Okay, but the voltage is anything but. This is done by effectively a pulse width modulated signal, so a digital signal, so that when it's smoothed, it gets the current sinusoidal, but the voltage itself is non-sinusoidal. It's very lumpy. Now, if we multiply voltage and current at each instance in time, we'll find the instantaneous power. And of course, if we take the average of this, that gives us the active energy. What you'll notice, some of these, the vast majority is giving us active energy, if you like, but there's some negative energy too. And that's where the reactive power comes from. Now, if we take those signals and we do a Fourier transform, we can see why that happens. So first of all, if we look at the current up here, we see it's nice and sinusoidal. But when we look at its PSD, we actually see that at the low frequencies, this is our sinusoidal wave. But we see that there's these harmonics coming in here. So this is the switching frequency of our inverter, and these are the harmonics. Now, in this case, we don't see them in the signal, because if we look, they're about 4 orders of magnitude lower than this dominant fundamental frequency. So we don't see them here. But when we look at the voltage signal here, we notice that they're comparable amplitude, which is why they're very clearly seen in this signal here. Now, when we look at this, we usually split it into 3. So around here, this is what we call the fundamental frequency. This is the frequency that's driving our electric motor, whether it's single phase, 3-phase, 9-phase, or whatever. And then up here, we've got the switching and the harmonics of the switching. And there's a gap in between where we could put filters if we wanted to. Now, if we were to calculate the active, reactive, and apparent power, assuming that they're purely sine waves when clearly they're not, then we're going to end up with difficulties. So this is the traditional way of calculating the power, assuming that they're sine waves. So first of all, the apparent power is the sum of that. It's kind of like the best case scenario of both the active and reactive together. So if all the power was useful, that would be the apparent power. And that's defined as the RMS of voltage times the RMS of current. So you see there's no phase difference in this. That's why we get it. Now, our active power is defined as the average of the voltage times the current. So that's taking the average under this curve here. And the best frequency we can get is the half cycle frequency if we're taking the averages of that. The reactive power we obtain from what we call the power triangle. So if apparent power is the hypotenuse and active power is one leg, then the reactive power is the other. And the power factor is how much of the useful power is actually the active power in this case, compared to the apparent power, how much of it is actively doing some good for us. And the problem that we've got here is when we look at this, because they're non-sinusoidal, and it looks like the reactive power is very high compared to the active power. In fact, the reactive seems to be bigger here than the active power. And this doesn't really stack up to what we're seeing in this diagram here. And the reason it appears wrong is because these simple equations, they're not accounting for the differences in these high frequencies. They're assuming that they're perfectly sinusoidal. Now, within the nCode software, we can actually take account of that and cover it for you. So now if we look at this, we can see the apparent power, we can see the active power, and we can see the reactive power down here, which is a lot more what we'd expect it to be. Now, again, we can do that with eDrive. And if we do it with eDrive, what we want to do is we want to put a filter really towards the edge here, a low pass filter. So we want to get rid of these high frequencies to make it a sine wave, really, as close to a sine wave as we can get. And that way we'll get the correct results there. But in nCode, that's all handled for us. And what's more, nCode uses a different approach. Rather than taking an average where we're limited to only getting the half rotational cycle frequency, within the nCode software, we can also use a method called the Hilbert method, where we can actually go and we can start to calculate active, reactive, and apparent power right at the very high frequencies, the switching frequencies in the inverter. So by understanding what the inverter's doing, we can start to hopefully improve the way that efficiency is building up through our vehicle to look at that. So again, the benefits of this are that there's no sinusoidal assumptions. There can be any number of phases. And most importantly, because we've got those very high frequencies, it can all be done transient as well, with varying frequencies and amplitudes depending on where your foot is. So a lot more sophistication. So it's all about getting more and more useful data out of your laboratory system. So again, using post-processing means that we can achieve a lot more from those data, and they complement each other. Now, of course, just winding to an end here, not all data comes from a laboratory, and very often we need to work out what do the real customers use our vehicles for. And very often that means usually using Canvas and probably GPS data to try and work out what customers are doing. And again, in the nCode software, we can do that as well. So one of the things that we look at, we've used quite a lot, is looking at power from simple GPS data. So this is usually GPS logging at probably just 1 hertz, 1 sample per second here. And just see what we can get from that. So if we've got, say, a car that's accelerating up a hill over a fairly rough road, we actually know that the reactive force, the force we've got to overcome, is going to be the inertial resistance, so the mass times acceleration of the vehicle. We've got its gradient resistance, which is the mass times gravity times sine of the alpha, so that's its gradient. And of course, we can work out alpha from GPS by looking at the arctan of the change in altitude, rate of change of altitude divided by velocity. We've also got the aerodynamic drag in here, and we've got the rolling resistance as well. And if we sum those together, then we can actually calculate the theoretical force that's required. And if we multiply that by velocity, that gives us the attractive power. So GPS can give us a relatively accurate assessment of the power from the vehicle. Not relatively accurate. It depends generally in a car how many people you've got sat in it and whether you're towing anything. They're the biggest influences, the mass. But typically we can get sort of 5-10% probably the worst estimate. So between 5 and 10% accuracy on that. So why is that useful to us? Well, it actually means that we can start to see how customers are using their vehicles. So one of the analyses that we did was to look at city buses, which were hybrid. So they were hybrid diesel engine, also with battery packs as well. So typical information we can get from GPS-based data is the trip date, start and end time. Now, start and end time is quite important in the day when you've got a city bus, because that dictates what the traffic congestion is going to be like. We can also look at things like the trip duration and distance. We can look at all the different speed profiles. And in a bus, an important one is the idle time, the number of stop-start cycles. What's the stop duration? What's the running duration between each stop? How far does it spend on city roads, urban roads, highway, all from GPS? And we can also look at things like the active tractive power, braking power, the energy consumed, and the overall efficiency. And for those who are interested, we can even do things like cornering acceleration and steering angle as well when you're trying to get the road load data correlation done, which we were trying to also reproduce on proving grounds here. But more important to us is probably the histograms, because these will allow us to tailor tests and to check that our laboratory tests actually do encompass the range of customers that we're seeing. So things like the time or distance with respect to the road speed, or the acceleration or braking with respect to time, or the tractive power. How long was it in traction power? How much was that? The braking power, cornering acceleration, and so on. So we've got this wonderful capability just from GPS. And of course, in most electric vehicles today, we can also get logs from the CAN as well, the CAN bus. So this is telling us from the vehicle management system, the controller, we've got the data here, and we can compare those data between them, and we can start to detect problems. We can characterize usage patterns. We can compare those with our battery and motor testing in the laboratory and try and obtain better tests and so on. So there's a huge amount that we can do with the data. So this is by using the nCode software from HBK as well. So just to finish off then, so in this webinar, we've looked at electric motor efficiency and loss mapping. And we've seen how we can do that first by gathering data from the eDrive system and then post-processing that data to get those efficiency maps that we can then play games with. We've looked in particular at power measurements and analysis from the digital inverter, because that's the thing that really we've got most room to play with to try and improve the way that we get efficiency from our vehicles. But we've also had a look at using real-world battery data as well. And also I've talked a little bit about how we can do target customer analysis. So to characterize the customers to make sure that our tests are better representative of the people who are buying our vehicles. So the benefits of this is we should hopefully get better vehicle range, much better accuracy in the measurements and the calculations, and a better understanding of really what customers are doing with our vehicles.